Anywhere you find a wireless device, you'll find batteries. It could be a battery pack in your laptop or your phone, could be alkaline batteries in your remote control, or even coin cell batteries in your hearing aid. Alkaline batteries may not be strong, but they are incredibly versatile and they are incredibly smooth, one of the most even and gentle power supplies available. The way these batteries work, these alkaline batteries, there's chemistry inside that causes a charge separation. It forces electrons to the negative end, which causes a dearth of electrons from the positive end. That charge separation causes potential difference voltage, which when you connect to a circuit creates an electric field and creates electricity. Inside, you've got salt bridges and positive and negative ions flowing around and fancy stuff. But very simply, it just pushes electrons to the negative end, takes them from the positive, and there's your power, just waiting to be used. Now, if you connect two batteries in series, their voltages add, and you might think the power is flowing through them, but it's not actually. The electrons are coming out of the negative end of this battery through your circuit. They're going in the positive end here, but in between here, you've just got electrons from the negative here zipping over into the positive here. That's all you've got. So conceptually, the charge is flowing through the batteries. But in reality, it's just the charges that are touching equalizing. The outer ones are being equalized by the circuit. The inner ones are being equalized between each other. That is why you can put batteries in series when you should not put any other power supply in series unless it is designed for it specifically. Batteries are the safe ones. When you put them in parallel, it's much easier. You just have them coming out together, going in together, and it's very easy. Batteries in series add their voltages. Batteries in parallel split their current, so part of the current is coming from each. The reason you have batteries in series is if you need more voltage. The reason you have batteries in parallel is to make them last longer. Batteries have something called internal resistance. If you short the terminals of a battery to each other, it is effectively, conceptually, a short circuit. But in effect, it's not. This internal resistance can be represented with a resistor. And then let's say that this is just the load of your circuit, whatever work is being done. So your battery connects as if you had this. So essentially, a battery can put out only a certain maximum amount of current for any particular voltage configuration. For example, one battery is 1.5 volts. So you have resistance that's dependent upon the chemistry in the battery, the structure of the battery, which at 1.5 volts is going to give a minimum resistance for your entire circuit, which is going to give you your maximum amplitude. Any resistance you add is going to further decrease the amount of power that this can put out, or will put out. But even if you have nothing at all, you have no more resistance added, you still have whatever resistance is in the battery. Let's put our load back. And if you add another battery, you also have another set of resistance in that battery as well. It's part of the battery's chemistry, you can't get rid of it. So when you connect a battery in series like this, you will double the voltage, assuming they're the same battery, in the same condition. You will double the voltage, but you will also double the resistance. Remember that your current, according to Ohm's law, is your voltage divided by the resistance. If you double your voltage and double your resistance, you're multiplying it by 2 over 2. 2 divided by 2 is 1, so you're multiplying it by 1. So you double your voltage, double your resistance, you get the same current. That is why you put batteries in series only when you want additional voltage, but you get the same current. If you put your batteries in parallel, then you still have your batteries, you still have your resistance, but the resistance is applying only to that battery. So you combine them, like so, with junctions. Each battery connects with only its own resistance, and they are connected together through the load resistance, if any, and there's none if there's a short circuit. So this resistance is dropping this voltage, this resistance is dropping this voltage. They're not dropping each other. So what you have is the same amount of voltage as you would with a single battery. They don't add because they're not combining their pushes, so to speak. But the current is split, and so you'll end up with roughly half the current in each. And we can verify it mathematically if you remember Kirchhoff's law of voltage. There's a loop here where you have, let's say, plus 5 volts. Well, no, let's say plus 1.5 because it's an alkaline battery. So we'll say plus 5 volts here. And then this resistor and this resistor are dropping that 1.5 back down to 0 to get back to here. And the same thing for this loop around. but this resistor drops voltage one time. It can't be different for each of these calculations. The only difference would be these resistors, and you can see that those loops are independent. Kirchhoff's law of voltage says no matter what loop you draw, you can go around here 3 times here, back and forth, it doesn't matter. As long as you draw a closed loop, you will get a total of 0. So one important thing is that when you have batteries in parallel, like this, they always read the same voltage at all times. If you have these two voltages different, one of the batteries, the one with the higher voltage, will actually be pushing current backwards across the battery with the lower voltage. So you will in effect be charging your other battery. Now when the voltages are only a tiny bit different, that is insignificant. It doesn't matter if we're millivolts off. That charging is not going to generate that much heat, that much gas inside the battery. It's negligible. But if you start having major differences, then you're going to have trouble. If for no other reason than your circuit is operating inefficiently because your batteries are pumping into each other and there's always waste in any sort of current transfer. So you're wasting energy that could be used to power your device. And in the worst case, your battery is going to heat up a little bit, but especially it's going to produce gas, which is going to burst the battery, and you'll have a mess inside your battery chamber. So the advice is always to use batteries together that are fresh out of the box and the same manufacturer. And this is the reason, because different structures of the battery, slight differences, can cause the voltage to drain at different rates. So even if you measure the voltage of 2 different batteries at the same value, close enough, and one of them's Rayovac and one of them's Energizer or whatever, then as time goes on, they might drain at different rates. One of them is going to charge the other a little bit, which isn't going to hurt anything in the short term. Again, it's only a small difference. It's going to try to equalize that difference as soon as it happens, but that's going to continue to happen nonstop as one drains faster than the other. So you're constantly going to have a trickle charge going from one battery to another, whichever one is draining slower into the one that's draining faster, because that's how batteries drain, the voltages go down. And eventually you're going to have a popped battery, probably. If you're only using your batteries for a short time, it doesn't matter. If you're constantly taking your batteries out when they're not in use, it doesn't matter. But if you're leaving batteries in a device for a long period of time, follow this advice. So I have here prepared 4 1.5 volt AA batteries so we can do some demonstrations. But first, let's do some quick tests. First of all, to get a rough idea of how much voltage you have in a battery, and therefore how much charge it has, you just measure the short circuit voltage across the battery. Red probe goes on the end with the nubbin, black goes on the other. Read it across, and you get 1.593 volts off of a D-size battery, 1.604 off of a C-size, 1.574 off of a AA, 9.39, 9.40 off of a 9 volt, 1.513 off of a AAA, and now the fun ones, the coin cells. This coin cell, which is a CR2032, which is labeled as 3 volts, gives you 3.03 volts. This one, which is a LR44, I think that says G, with no marked voltage, gives you 1.57. So you can see the difference between these batteries is mostly just how big they are. Now, what effect does that have, you say? First of all, it obviously has an effect on their capacity. So let's also measure the short circuit amperage. This is going to be higher than the maximum 200 milliamps of the normal meter setting, so I'm using the other one. The maximum 10 amps, which recommends no more than 10 seconds. We'll be doing far less than that. So if we measure the D cell, the biggest one, we get 3.1 some amps. A C cell battery gives 2.53. A AA, these are all still 1.5 volts. A AA gives 2.93. A AAA, the littlest one that's not a coin cell, gives 2.04-ish. So those were the regular 1.5 volt long type alkalins. How about the 9 volt? You'd think this one would go much higher, wouldn't you? Well, 2.49. Again, that's a quick reading. But you can see it's not much different. Go to the coin cells, however. Go to the 3 volt large one. 0.4 some, and dropping rapidly. The littlest one, this tiny little thing, 0.67. The coin cells are the kind of batteries you'll find in very low amperage, low voltage situations such as hearing aids, where you want them to last for a good while, be nice and small. I found one of these batteries, I forget which one, it was probably this one, in a little flashlight. It was a little keychain flashlight, just a dinky little one, probably cost $1 or less. You press a button and a single LED lit up. It's enough to find the keyhole in the dark, for example. And when I opened it up, to my surprise, there was a short circuit. They had taken this coin cell battery and they had taken an LED and they just taped it on. They just stuck the terminals of an LED across it, just like this. Let's see if we can demonstrate. Just like that. And because the maximum current output is so low from these coin cell batteries, it doesn't matter. They effectively had a resistor avoiding a short circuit in their circuit, their cheap Chinese circuit, in the battery itself. So as we've demonstrated, because the voltages are roughly the same, the amperages are roughly the same, that means their internal resistances are roughly the same, and the difference is capacity. The D cells last longer. So now we will simply demonstrate how to combine batteries and what the results are. So first, I will confirm the voltages of these 4 batteries to make sure they are plugged in correctly. So we will have 1.577, 1.564, 1.580, and 1.558. These numbers are all close enough that you could use them in a circuit safely together, since they are all the same manufacturer, in fact. The very small voltage differences would equalize rather quickly, and they would all drain at roughly the same rate, and you would not get any significant wear and tear on your batteries. So let's now combine all 4 of these batteries into one battery pack. We'll connect the negative end of one to the positive of the other, the negative of that one to the positive of this one, the negative of that one to the positive of this one. And then we'll connect our probes at a higher voltage setting, of course, the negative end here, the positive end here, and as you see, 4.71. And we wouldn't get any voltage if it weren't a complete circuit, but you can see just how much resistance is happening, because that should be 6. If you connect the batteries directly to each other in a battery pack with electrical tape, you won't get that much resistance. But this is going in and out and in and out and in and out of these not the greatest conductor traces inside this breadboard. So the added resistance is causing a drop in voltage. Just to show, I will quickly tape together 2 batteries. And with these 2 batteries directly touching each other for minimal resistance, our voltage reads 3.16. So you can see why a breadboard is used only for prototyping and not for actual circuit building. So now I will demonstrate the effect of adding amperages. If I were to take one battery and measure the amperage across it, we will get roughly what we did before, but it's worth checking again because now we're in a breadboard, so we have that resistance. And again, do this quickly because it's draining power very fast. In this breadboard, one battery produces about 1.3 amps. You'll notice that it's significantly lower than before. But what if we connect 2 in series? So the negative of one to the positive of the other, and then we connect our probes, negative here, positive here. We get 1.25, 1.26. And it's difficult to tell because of all the resistance in here. But what we had was 3 volts instead of 1.5, and we had double the resistance. So once again, the amps should be about the same. Double voltage, double resistance, the doubles cancel out for about the same current. Now let's connect them in parallel. So I will take the positive of one to a new shared rail, positive of the other to the same rail. Then we'll do the same with the negatives. The negative of this one to a shared rail, and the negative of the other to the same shared rail. Every wire, every trace I go through adds resistance, but that's fine. We will now measure the amperage. Connect to the negative rail, connect to the positive. We're getting 1.59. You'll notice it has gone up because each battery did not increase its voltage, did not increase its resistance within its own part of the circuit. So they're each contributing their current according to this. And the numbers are off again because of all the resistance of the wires and the traces. So let's do the fanciest thing yet. Let's do a 2x2. So we will have a 2x2 battery pack, which is 2 batteries in series, 2 other batteries in series, and then in parallel. You wouldn't want to do it the other way. You wouldn't want to connect these 2 in parallel and these 2 in parallel and then do it in series. That would just be silly. You could do it, it would function, but it would be silly. So to accomplish this feat, I will first connect 2 in series. So the negative of one, positive of the other, and then I will connect the positive of the first one to a new shared rail, and the negative of the second one to a new shared rail for the negative. Then, for the second pair, I'll do the same thing. The negative of the first to the positive of the second, then the positive of the first to that shared rail for positive, the negative of the second to the shared rail for negative. And we will first measure volts. So if I connect to the negative and the positive of that rail, we get about 3.12 volts. So with everything connected together, like this, we're getting much less resistance. They're able to push through it more. So now let's measure the amperage. Negative into the negative, positive into the positive. We get roughly 2.1, 2.0 amps, as you would expect. And that about says it all. Connect batteries in series if you want more voltage. Connect them in parallel if you want to share the amperage between them so that your batteries last longer, or that they can provide enough amperage so that your circuit even works. Though you shouldn't be using batteries near their full output anyway, because that is so rough on the battery, they will fail much earlier. An actual power supply, a bench power supply, or something like a wall wart that you plug in, like your wall charger for your phone, is, of course, much more easy to work with, much more configurable, but no matter how hard you try, it will never be quite as smooth as a battery. So just pick whatever works for your situation. And until then, be seeing you.